I'm Ryan from Indiana University, and I'm going to talk about some work that I have been doing on making information theoretic PIR more efficient using batch codes. So we've seen two different styles of PIR, now we'll see the third. So I'm going to very briefly go over the PIR problem because I think by now you all know what the PIR problem is. We have a user, Bob, here who is trying to fetch some information over the internet. Typically, he's going to send some request to a remote server and get some sort of response. And this being pets, we're interested in providing some notion of privacy for the user. In particular, we're considering scenarios where, for example, Bob is trying to research a super secret patent idea that he has. He wants to find out, is this novel, before he devotes the next 6 months of his life to working out the details. And he's worried that perhaps this remote server might infer what his idea is and patent it before he's actually finished. So we want to make sure that we can allow these queries, but provide privacy to prevent this sort of attack. And the approach we're going to take is actually the very first approach with some tweaks, the very first PIR approach. So we have a database, which we're going to model as a matrix. It's going to have R rows. Each row is going to be S words long. And what the user is trying to fetch is one of the rows from this matrix. So it's just a matrix over some finite field. And the way we're going to represent a query into this matrix is using a vector from the standard basis. So this vector is going to be a length R vector, where R corresponds to the height of that matrix. It's going to consist of all zeros except for a 1 in a particular position, which corresponds to the row that the user is trying to fetch. And we'll define the result of the query to be the product of that vector with that matrix. And for those of you that remember your basic linear algebra, it should be pretty easy to see that if you multiply that vector times that matrix, what will pop out is indeed the jth row. Okay, so this seems to work, but we don't have any sort of privacy. So we need to do something here to get privacy from this. And it turns out this is actually relatively simple. So the approach we're going to use was proposed by Goldberg back in 2007. We're going to replicate the database, as was previously mentioned, amongst several different servers. And then Adi here is giving us the missing piece. We're going to use his secret sharing scheme to take this basis vector, which is clearly non-private, and secret share it component-wise. So we're going to take each and every entry in this. Why isn't it going? We're going to take each and every entry in this vector, and we're going to use Samira's secret sharing scheme to turn them into vectors that look essentially random. We're going to send those to the servers, and then we're going to wait and wait and wait and wait while these servers multiply these random looking vectors times the copy of the database that they have. And hopefully sometime soon, because I only have 15 minutes for this talk, the servers will come back with their responses. And because everything here is linear, the secret sharing is linear, the vector matrix multiplication is linear, the user just has to do a component-wise reconstruction on the responses, and lo and behold, what pops out is the record that the user was after. But from the perspective of any individual server, clearly they can't figure out what the user was after. And in fact, the number of servers that would have to work together to figure out what the user was after is the same as the number of servers, or the parameter that was chosen for the secret sharing, the reconstruction parameter. So if we make an appropriate non-collusion assumption, we can prove that it is literally impossible for these servers to de-anonymize the query. So what I'm interested in was that step where we waited and waited and waited and waited, and seeing what we can do to reduce the amount of time we have to wait. So yippee, we have PIR. Can we get to the new stuff? Yes, we can get to the new stuff. So the basic tool we're going to use is called a ramp scheme. For those of you who aren't familiar with ramp schemes, I'm just going to go over it very quickly. It's a very natural generalization of secret sharing schemes that have actually been studied as long as secret sharing schemes have, but don't show up in applications quite as often. So in a typical secret sharing scheme, we have some parameter, I'm calling it T here. If the attacker gets their hands on T or fewer shares, they learn nothing at all about what the secret is. But as soon as they have T plus 1 or more shares, they have the entire secret. And a ramp scheme just relaxes this so that if you have T or fewer shares, you still have no information about the secret. But in order to get complete information about the secret, you now have to have T plus U shares, where U is some parameter that's at least 1. And the upshot of this relaxation is we can now fit U secrets, or U times as many secret bits, into the secret sharing scheme. So the shares that the users have look exactly like they used to, but we have a U-fold improvement in the amount of information we can pack. And we're going to try to use this to speed up the PIR. And how do we actually implement this? So if you think of Shamir's secret sharing scheme as you have a random polynomial, it's random other than the y-intercept, which encodes a secret. We're going to do basically the same thing, except now the y-intercept encodes a secret, and perhaps when you evaluate the polynomial at x equals 1, you get a different secret. We could pack another secret at x equals 2, etc. So in this example, there's just 2 secrets, and I'm going to set t equal to 2. So to make the polynomials we use for our ramp scheme sharing, we just throw a couple of other random points on there, then we interpolate through these, and then we evaluate the resulting polynomial at some other points and hand those out to the various shareholders. Okay, so how do we use this to speed up PIR? So there's actually 2 different things that I'm going to talk about. One of them is new, one of them is old, and then the third thing is how we glue those together to get a really fast protocol. So the first idea, the new one, we take our R by S matrix. And the first step is just a rewriting step. So we're going to think of it as a bunch of U by S matrices stacked on top of each other. So right now I'm just rewriting, changing notation, but I haven't actually changed anything. Then from there, we are going to take this collection of U by S matrices, and we are going to turn each matrix into a set of ramp shares. And typically you would just set the privacy parameter to 0 here, but there are cases where you might want to set it higher. I won't talk about those, but the paper discusses it a bit. So what we're actually doing here is we're taking one column of this matrix, we're interpolating through it to get a polynomial of degree u minus 1, and that's the first entry here. And the second column of this becomes the second polynomial here. So again, this matrix is a new representation of this thing, but it's equivalent, right? It's just a different representation. It's very easy to go from here to here, and it's very easy to go from here back to here by just evaluating these polynomials and putting the results in the right places. The next step, things change slightly. So we're going to take this matrix of polynomials, and rather than handing out the entire matrix to each of the servers, we're going to evaluate it and hand out evaluations to the servers. So the first server is going to have this whole matrix evaluated at some x-coordinate. The second server is going to have it evaluated at some other x-coordinate, and so on. And so now suddenly each of the servers, rather than holding an R by S replica of the matrix, holds an R over U by S matrix of scalars. So this is much smaller. I mean, at least half the size if you set U equals 2, and even smaller if you set U higher. And so now we need to figure out how do you actually get something out of this bizarrely encoded PIR database. It turns out this is pretty simple. So we're going to take the index of the record we're after, and we're just going to figure out from that which polynomial contains the record that we're looking for, and at what value do we need to evaluate that polynomial to make the record we're looking for pop out. And this is very simple. You take I and you try to divide it by U, and you get your quotient and remainder. And the quotient is going to tell you which row in this polynomial matrix contains your record, and the remainder is going to tell you what x-coordinate you need to evaluate that polynomial at to get the record you were after out. Then we're going to do essentially the plain old secret sharing PIR query, except we're going to use this shorter standard basis vector that we get from the quotient, and rather than having the y-intercept of our secret sharing polynomials pass through this, we're going to have the point at x equals whatever that remainder was, and then everything else works out exactly as it used to. And when we look at the costs of this protocol, we find that compared to the original protocol I started, we get some nice performance improvements. Basically, the upload, computation, and storage costs are each decreased by a factor u for whatever you set that u parameter to. Okay, so that's pretty nifty. What's the trade-off? So I've only got 15 minutes. I'll get back to that later. The second thing we're going to do is figure out how can we get more information out of the database at the same cost. This is actually work that I did with Ian Goldberg and Icho Huang back in 2013 that I'm going to talk about briefly, and then we'll see how it can work with this. So the idea here is rather than sending a vector like this, we want to fetch several blocks. What we really want to do is send a matrix that has a whole bunch of different queries into it, but we want to try to do this sort of as efficiently as possible. This was where we first came up with the idea of using ramp schemes. We thought rather than component-wise sharing this matrix, why don't we use the ramp scheme and turn this into a single vector and send the resulting vectors of scalars rather than matrices of scalars to the servers, and we get a nice speed up. So here we have this matrix, we turn it into a vector of polynomials rather than a matrix of polynomials. We send a vector to each server, and when you do that, we found that you also get a nice speed up. When we pack Q rows into the ramp scheme polynomials, we get a factor Q speed up in the upload, download, and computation cost. So that's quite nice. But again, what's the trade-off? And again, don't worry about it. Okay, so the next thing I want to talk about is what happens if we try to put these things together. And it turns out you can use this, what I call the U-area encoding, this taking the database and encoding it in these ramp scheme polynomials with those Q-batch queries. And then if you add in some other very important subtle details, which I will just sweep under the rug for the time being, you get Q blocks for the cost of 1 over U blocks, which is quite nice. So what are the important details that I'm sweeping under the rug there? If you think about this encoded matrix that I was talking about, you can kind of view it as a 3-dimensional matrix. So we have R over U rows, S columns, but then we have, for lack of a better term, U slices to this. So if you evaluate these polynomials at 0, you get this set of R over U records, and if you evaluate it at 1, you get a different set of R over U records, and so on. And if you think about how you query this thing, well, if we want the ith block from the jth slice, the way we actually fetch that is we encode a particular standard basis vector at a particular x coordinate. And the annoying observation that comes from this is we can't actually use one of these multi-block, these Q-batch queries to fetch more than one block that come from the same slice, because we find ourselves in the impossible situation of taking 2 different basis vectors and encoding them at the same x coordinate in our polynomials. So this occurred to us, and we went, oh, darn, that's unfortunate, or to me, rather. And I went, oh, darn, that's unfortunate. But then I realized there's a very simple fix for this. Okay, yes, this is the cost of, I don't know, this is sort of out of place. Oh, okay, sorry, I eliminated a slide. So there's a very simple fix for this, which is basically to take each of these records and put them in their own slice. So we're gonna, rather than using the remainder upon division by U to figure out which x coordinate we put it in, we just take each record. So if you want record 1, you evaluate the polynomial at x equals 1. And if you want record 2, you evaluate the polynomial at x equals 2. So we still have R over U rows, but now we've sort of, you can't really draw a picture anymore. Yeah, but sorry, I think I botched that explanation, but hopefully you kind of follow. So if you want to get the record, you find the appropriate row, and then you evaluate it at the x coordinate corresponding to the true index of the record you're after rather than its remainder. And suddenly now we can fetch any record we want in a batch together, and we don't have to worry about these collisions at an x coordinate. So if that was not clear, please read the paper because it's clear in there. Okay, so when you do that, what we find is we get really nice speed ups in every reasonable cost metric. So to get Q blocks from one of these U-area encoded databases, we get a factor QU speed up. In 2 of the metrics, we get a factor Q speed up in the download cost and a factor U speed up in the storage cost, and everything is much quicker than it used to be. So I implemented this in PIR C++, the open source implementation of the basic PIR protocol I was talking about. And this is an arbitrary graph because there were so many moving pieces. I didn't know what to actually measure, but I thought this was nice and illustrative. So here we have the database size going up to about 256 gigabytes, and the server-side compute time. This is single core, so everything here is embarrassingly parallelizable, but the experiments only used 1 core. This top line is the cost to run the protocol with the default U equals 1, so the standard before I made any changes. And we see that the cost of doing this 256 gigabyte database on the particular computer I threw at it is up at around 1,000 seconds. When I set U equals 8, which seemed like a reasonable upper bound on the realistic size, we get a factor 13.5 speed up. We get more than the factor 8 speed up because I ran out of RAM at around this line. So in this case, everything fits in RAM, but here everything doesn't fit in RAM, and you end up getting some latency so that. So things are quite a bit faster. The upshot of this, so basically it takes about 0.2 seconds per gigabyte, so core seconds per gigabyte to process this database. If you have 16 cores, divide that number by 16. Things are quite fast. Okay, so I kept saying, don't worry about the trade-off, don't worry about the trade-off. Right now, I'll briefly touch on what the trade-off is. So when that original protocol by Goldberg was proposed back in 2007, the actual title of the paper was Improving the Robustness of Private Information Retrieval. And the main contribution was that the protocol could handle quite a few incorrect responses from the servers. So if you set that privacy threshold to be a little bit smaller than the total number of servers, then you can handle some servers not responding and some of the responding servers responding incorrectly, and use ideas from error correcting codes to make sure that you still retrieve the information you want. And so this was sort of the breakthrough, that you could get this Guruswamy-Sedan list decoding radius as your robustness level. If we fast forward 5 years, there's new techniques, new ideas, and this bound is increased quite dramatically. So the idea is, if you were happy with this level of robustness, but suddenly we just get this level of robustness for free, then we can reallocate some of that robustness to get better throughput. So at the end of the day, the user, or the servers, get to set these parameters however they want. L here is the number of servers, T is that privacy threshold. So what we want to do is keep L and T fixed. We want to say there's this many servers, this many of them can collude, and we get to play with these other parameters. I didn't talk about tau, but it's discussed in the paper. And the observation is, we can set Q and G however we want up until V gets down to 0. And so and V is the number of malicious servers we can tolerate. So by reducing this number of malicious servers, we can increase those Q and U parameters arbitrarily to whatever level we want. And as long as this equality is satisfied, everything will still work. So that was everything I wanted to take away, or wanted to say. My takeaway is that if you use ramp schemes in IT-PIR, you can get very fast-ish, still slow compared to non-private, but fast compared to everything else, private information retrieval. Thank you.
Okay, thank you.